So our topic for discussion today is fluid pressure and its measurement. We're going to talk about how this pressure is determined, starting with, first of all, analyzing the formula for pressure. Previously, we used it on Pascal's law. We basically picked it and applied it on hydrostatics, where we're talking about fluid that is not in motion. So we'll just try to review that formula and derive it from first principles so that we can see where that formula comes from. Because normally when you use a formula like that, it makes sense that you also look at where it is coming from. So let's see how we are going to do this. So first we are saying, when you talk about pressure, it is simply the force per unit area, force over area. Now this expression, this formula remains valid like that, meaning that if I have to make force the subject, it will be pressure times area. Static pressure, like you might have seen, is the kind of pressure which comes as a result of this liquid, which is above a given point. So you could be talking about the height h, and then what is the property of the liquid? What type of liquid are you having there? So you multiply the volume by the specific weight, then you get the force. Now, here what we have is this. Force is pressure times area. If you multiply specific weight times the volume, you also get a force. So these two can be equated. Now we also know that when you expand this one, volume is area times height. So putting it back in the formula, you have pressure times area being equal to specific weight multiplied by area times height. Already when you check, you can see that the area is common on both sides. You're already having, here there is area and there is also area. So we can now make pressure the subject of the formula. So then our pressure is specific weight times height, omega times height. So that is how come that formula we were talking about last time, where we're using it to calculate the static pressure and the pressure due to that weight of fluid acting at a point. This is where it comes from. So we always ask once in a while that, can we prove where this is coming from? So it's as simple as that. We review because we know that the force acting is the same. The force acting at that point is the same. Then from there, we just expand and cancel the common, and there we are. Now, we have what is known as atmospheric pressure. What is atmospheric pressure? This is the atmospheric pressure can be defined as the kind of pressure exerted on objects by the atmospheric air. And the average value, the value that we'll be using for analytical purposes for calculations, is 100,000 pascals or 100 kilopascals. But the actual average value is 101.3 kilopascals. No need to worry about that because we'll be focusing on this in the calculations that we'll be using. This is the number we'll be using from time to time. We also have what is known as gauge pressure. The first word here is saying gauge, meaning that when you are measuring this type of pressure, you're using a gauge, using gauges. So the kind of pressure you measure with the help of gauges, that is your gauge pressure or pressure measuring instruments. In other words, you take your reference pressure as atmospheric. You'll use the atmospheric pressure as your reference pressure, or your zero. Your zero is the atmospheric pressure. What you measure above or below that is the one we call gauge pressure. Now, to correct this, we have what is known as absolute pressure. With absolute pressure, we add these two because we are saying that in our calculations, depending on the analysis we're doing, we may not ignore the atmospheric pressure. So we add the atmospheric pressure to the gauge pressure. Then the total, the answer we get is the one which is now the absolute pressure. So that is our formula. Absolute pressure is the sum of the atmospheric pressure and the gauge pressure. Here you can even put your 100,000 in advance, then whatever value you get there, you just add, then you are there. Because we know that the average value, the value we're using for atmospheric pressure is 100,000. And even when you hear that the pressure is 1 atmosphere, they are referring to this value, meaning 100,000. When you are trying to measure the fluid pressure, when you want to determine the pressure of a fluid in a column, in a vessel, or at a point, you may use manometers or mechanical gauges. You may use what is this available for you. It could be manometer or mechanical gauges. So these, for now, we'll take our time to analyze the manometers. So what manometers do is simply to use a column of fluid, balance it with another one, then from there, you are able to determine the pressure. And we have 3 types. They are what we call single column manometers or piezometers. We have U-tube manometers as well as differential manometers. These are the 3 types. With differential manometers, we still have 2 further types where we have the inverted and the normal type. So this is the piezometer. In a piezometer, you have a pipe. So remember, a pipe looks like this. Then on one end, if I was to look at it from one end, this is what I will see. So what we are doing here now is that you've picked this piezometer. You drill a hole on one side, and then you insert this tube. So when you look at it from this end, this is what you see. So you have that manometer from the center going up. As you see liquid rising, that is what gives you the pressure. So the pressure will be given by specific weight times the height. In this case, that is the height. We also have what is known as a U-tube manometer. Where the U comes from is just because of the shape. This is a U shape. So with that U shape, we have that manometer. So here is the liquid flowing at the center of your pipe. That is your pipe there. And then you insert, here you have an opening, then this is connected. This is the liquid from the pipe. On the other side, you have the liquid in the manometer. It's mercury this time. It can be another liquid another time. But what we have is a different liquid on this other side. So you have the right-hand side of the column and the left-hand side of your manometer. So then how do you determine the pressure? All we know is that the pressure at X is equal to the pressure at Y here. So the pressure at X is equal to the pressure at Y when we apply Pascal's law. So let's start with the pressure at X. The pressure at X is equal to the pressure inside the pipe plus the pressure due to this height of liquid. So PA plus omega H. What about the pressure at Y? The pressure at Y is simply specific weight times this height. Which is specific weight? The specific weight of this liquid. To differentiate it from the other one, we call the specific weight of this one as W1, or rather omega 1, because we want these to be identified without problems. Having done this, let's apply Pascal's law. Because we said with Pascal's law, the pressure at this point is equal to the pressure at that point because they are at the same level. Then we can express what is on the right, we just equate them. So PA plus omega H is equal to omega 1 H1. So here, this is what we have. But remember, the question is asking you to find the pressure of the fluid flowing in the pipe. What is the pressure, the fluid pressure inside this pipe? So make PA the subject. All you do is make this the subject. To do that, move this to the other side. So you have pressure at A is equal to omega 1 H1 minus omega H. Then we also have a U-tube manometer. This is the differential YouTube manometer. The importance of this one is to determine the difference in pressure between 2 points in fluid flow. When fluid is there, you need to know how much pressure is at here, how much pressure is there. But what is the difference in pressure between these 2 points? That is where this differential manometer comes in. So again, we're going to apply Pascal's law, where we'll say pressure at this point is equal to pressure at that point. Pressure at X is equal to pressure at Y. What we did on the other YouTube manometer, we just had this side. The other side, because it was exposed to the atmosphere, we just multiplied the specific weight by the height of the liquid. But this time around, we also add pressure at B. So pressure at X is the specific weight of this liquid times this height plus the pressure at point A. So this is what we have, pressure at A plus specific weight times height. We have to do the same for point Y, where we'll say pressure at Y is specific weight 1 times H2 plus specific weight times height. So pressure at Y, so there you have specific weight times height 1. So this is H1. Specific weight times H1, then specific weight to 1, which is this mercury here, times H2, which is this height. So this gives us the pressure at Y. Let me go through this again. We're saying that the pressure at X here, the total pressure acting at this point X, right here, has 2 effects. The first one is due to this weight of the liquid above it, which we will say, to get it, we use the formula for static pressure, which is specific weight times height. So that is it, specific weight times height. In addition to that, this pipe also has pressure acting inside it. So that is the one we're going to say pressure at point A. We just call it PA. So meaning the pressure at X, therefore, is PA plus omega H. This specific weight is for this liquid flowing here. We do the same for the pressure at Y. This is equal to pressure at B plus the specific weight of this liquid times height here. Specific weight of 1 times H, this is H2, plus the specific weight of this liquid flowing in the pipe. In this case, we assumed the fluid flowing here and the fluid flowing there, they are the same. It's oil. So that's why they are all, both of them are carrying omega. So specific weight, which is omega, times H1 there. That is representing this height here. So you put together the intensities of the pressure as a result of those liquid columns above Y plus the pressure at B. What do you do next? We can now apply Pascal's law. So we equate the pressure at X and the pressure at Y, meaning we pick what is on the left-hand side of this equation, just write it here, and we bring what is on the right-hand side of this equation, we also plant it there. Then we will need to make PA minus PB the subject, meaning I need to move this to the other side of the equal sign. And this should also move away from here. So then what I'm going to have is PA minus PB equals specific weight 1 times H2 plus omega H1 minus, because this is the one that has moved to come to this side, minus omega H. So these, you'll be given the numbers for all these. Once you plant those numbers, you get the value for the difference in pressure. Additionally, when you're given one of the pressures, you can also get the other pressure you're looking for. Here is our example. It says, YouTube manometer is used to measure the pressure of oil of specific gravity 0.85 in a pipeline. Now, The left end is connected to the pipe, the other one is exposed to the atmosphere. Then we're told the center of the pipe is 80 millimeters above the level of the mercury in the left limb. Oh my God. This sounds like a mouthful. Let's try to understand this. 80 millimeters above mercury level, where? In the left. So here is our manometer. The center of the pipe is 80 millimeters above the level of the mercury here in the left limb. This is left, this is right. So drawing it, that is what we have. What else? We are also told the difference in mercury level between the two limbs is 180. Again, meaning that this is mercury, this is mercury. The difference in mercury level, this is the level in the left limb, this is the level in the right limb. The difference between them is the height above here, because you subtract this from the total. In other words, I'm saying from here to here, that is my height in the left limb. Then from here all the way to there is my height in the right limb. If I subtract this height minus this one, what I get is this. It's like just chopping away this thing below here, this height below. And that is the one they have given us as 180 millimeters. In short, when they talk about the difference in mercury level between the two limbs, just take that level above that lowest level, then there you are. It can also be the other way around for negative pressure. So that is what we have there. It's like you subtract the two levels, then that is what. Now, let's arrange our data. The specific weight of the, first of all, we're given the specific gravity of this liquid flowing in the pipe. It was 0.85. To get the specific weight, we multiply by 9810. What we get is 8338.5. Next, we were told the height here, h is 80 millimeters. Convert it to meters, just divide by 1000. That's our h, becomes 0.08. Then this is our, we can call it our h1. That's my handwriting. That's my h1. My h1, okay, we'll come back to it. My h1 will also convert it to meters, it will be 0.18. Then we're told that this liquid here, the specific gravity is 13.6. Same procedure, we multiply by 9810. Where is the 9810 coming from? 9810 is the specific weight of pure water. And we define specific gravity as the ratio between the specific weight of any given substance and that of pure water. Now, since we're looking for the specific weight of that substance, we just cross multiply, because the specific weight of water is 9810. This is one item that we discussed when we were dealing with the properties of fluids. So you don't need to worry, we just multiply by that and we are there. So here we said we also convert H1, divide by 1000, we have 0.18. Then what do we do next? We go back to this at point Y. My pressure is specific weight times height plus PA. Then this other side is specific weight times height. When we make PA the subject, like you saw in the expression we had for a YouTube, we ended up with omega-1 H1 minus omega H. So we can just substitute. Omega-1 is this 133416. In other words, we are saying this is our value for mercury. So 133,416 times 0.18 minus the specific weight of the liquid in the manometer times the height, which is 0.08. So what do I get? Once we subtract there, we get 23,347.8. The question was asking for the absolute pressure. To get the absolute pressure, we said you have to add the atmospheric pressure. So the absolute pressure, we add the gauge pressure and the atmospheric pressure. The value we've just found is our gauge pressure. So we said the atmospheric pressure, the value is 100,000. So we add to this, and therefore our final answer is 123,347.8 pascals. Here is another question. This is now our inverted U-tube manometer. So what do we have? We are told that this is an inverted U-tube manometer. And to make it interesting, yes, there. Inverted U-tube manometer is like this. And what we've been given is that what we have up there is oil, whose specific gravity is 0.8. And then here, what is flowing on the other side is water. Since what is flowing here is water, that's why the other values haven't been given, because water is basically standard. You don't need to stress about it. It's a standard fluid. Now, what do? We need to find the difference in pressure between A and B. And also, if the pressure at A is 2 meters of water, then what will be the pressure at B? So let's get to work then. With that information, the data that has been provided, specific weight of water is standard. It's 9,810, like we mentioned earlier. For oil, we multiply the specific gravity. Even if we've been given the relative density, we carry out the same procedure. So the specific gravity times 9,810, then what we have is 7,848. H, this height here, we'll call it as our H. We convert it to meters, we just divide by 1,000. What we have is 0.3. H1, referring to this one, it is in 100 millimeters. Do the same thing, divide by 1,000. What we get is 0.1 once again. Let's do the same for this one. We'll call it H2, height number 2. If you divide 150 by 1,000, you get 0.15. So with this, we've exhausted our data. Let's now pick them one by one. Now here, we know that pressure at X is equal to pressure at Y. But we need to go for equilibrium, because pressure at A, we can get the intensity of pressure at A by adding everything else up here. Even the pressure at B, the same thing. So let's see then. Pressure at A in pipe A, this is where we are saying it is equal to pressure at A equals specific weight times height plus whatever pressure is acting at X. So specific weight multiplied by height plus the pressure at X. Just like what we had when we connected to a pipe, where we're saying pressure at A, this was the other one. So you add the specific weight times the height due to this, this height, 0.3, and then you add that pressure at X. Then you just turn things around, because you want to come and apply Pascal's law. So what you're going to do now is make pressure at X a subject. So to be PA minus C omega H, and you leave it like that. Let's do the same for the other side. This other side, in fact, here we plunk the number, specific weight of this liquid here, which is water, times the height there is 0.3. Then the number is PA minus 2943. Let's do the same for pipe B. B is specific weight times that height plus specific weight times that height plus the pressure acting at Y, which is at that point. So these are the ones you are going to add together. And with that in mind, you can just go ahead and start now planting those. So, oh yeah, this is, you know that this is actually a minus. Just like this plus C, let me just put it there. It's actually here, adding the two items together. So PB minus all that. So what do you do next? We want here, when you make this equation, the next thing you do is to make PY the subject, meaning they just switch positions. It's like everyone else moves to the other side. So pressure B minus these other ones. Pressure P minus omega H1 minus omega 1 H2. Then we have pressure at Y equals, we plant the numbers. Specific weight of this liquid here, rather there, is 9810 times 0.1 minus specific weight times Z. In this case, it's 7848 because we're dealing with the oil times 0.15 up there. So there you have it. It is now PY is PB minus 2157. So as a result, you can now apply Pascal's law here. Pressure at X equals pressure at Y. So what you're going to do now is to equate this to that. Because we've already said this left side, they are the same. The notice on the right hand side should also be the same. So then PA minus 2943 is equal to PB minus 2157. So this can cross the equal sign just as this can also cross the equal sign. And what does that give us? 2943 minus 2157. On the other side, you have PA minus PB. So with that, you get the difference as 786 newtons per square meter. That is our answer. Next, the question was asking, here you can see that we have PA minus PB, meaning if I'm given any of the two values, I can find the other one. That is for part B. So here we're given that pressure at A is 2 meters of water. So multiply 2 by the specific weight of water. That's what I have. So then if this is the pressure, I have to substitute back in this equation. So that's it. 19,620 minus PB is equal to that. So I'm looking for pressure at B. So meaning I can let this come to there and this move to there so that I have a positive. So what I will have is 19,620 minus 786. And hence, the pressure at point B is 18,834 newtons per square meter. You can prove this answer by planting back these here, where you put this one, which is 19,620, that's pressure at A, minus 18,834. The answer will still be 786 newtons per square meter. So that is how you handle an inverted differential U-tube manometer. If it is the other U-tube manometer, which is not inverted, you just flow like we did in the analysis, plant them, and there you will not need to start switching them around because the expression will be almost direct. So you will not need to struggle in that case. All right, next we have these questions with planted answers. I've put about 5 of these questions. You can take your time to go through the questions and let me know where you need to clarify. Once again, if you see anything that requires to clarify or you have a comment, reach out to me or plant a comment in the comment section. I'll be able to reach out in time.